Take it away, Byeongsu.
Okay. First of all, thanks to the organizer of Categories and Companion Symposium very much for inviting me as a speaker. And moreover, thank you all your attendants for attending my talk. So please feel free to ask me any questions if you have. So today I'd like to share a contravariant functor appearing on monomial ideas of affine semigroup rings. So this is joint work with Laura Matsevis. So yeah, indeed, what I want to say today is to help you understand the topological space, a standard monomial space, arising from quotients of affine semigroups. Indeed, my area of research is commutative algebra, especially using combinatorics. And unless I'm a big fan of the category series, but I'm not expecting that this kind of functor came out in my researches. So I just want to explain this, how this contravariant functor came up, then how this functor gives us the topological space, which give us some understanding of the combinatorial Cohen-Macaulay criterion for quotients of affine semigroup rings by monomial ideas. So to understand this notation, so this K is a field, and Q is affine semigroup, and I is a monomial idea in the affine semigroup rings, which I explained in the later slide. Then when we just localize these monomial ideas by a face of monomial idea, which is also I explained in the later slide, then it gives us some kind of the reverse map, injection map between the saturated curves of the IF and saturated curves of the I, which is called standard pairs of I. So the standard monomial space is nothing but just screwing those curves. And it is a crucial role on combinatorial Cohen-Macaulay criterion, and especially for finding the quotient of affine semigroup rings. So it was only known for affine semigroup itself by Trung and Hoa in 1986, or only the special cases of the quotient when the affine semigroup ring is isomorphic to the polynomial ring, which is called Stan-Nielsen ring, are known by Hochster and Lisner in 1977. So to elaborate what I said in this goal and motivations clearly, I will discuss this blue word, affine semigroup, and standard pairs, and standard monomial space, and Cohen-Macaulay in the following slides. Okay. So let's start with affine semigroups first. So given finitely many integer vectors, alpha 1 to alpha m, an affine semigroup Q is a set of all non-negative integer linear combinations of these vectors. Or you may think it as a span of alpha i's by natural numbers. So indeed, definitely it is a monoid since it has an additive identity 0, but traditionally it is called affine semigroups. And like a ring, monoids already have some ideas. So set I is ideal. If for any alpha in Q, alpha plus I is contained in I, then it forms an ideal. So you can think this cross as multiplication in the rings, and the definition is clear. Then ideas of Q have one-to-one correspondence with monomial ideas in the affine semigroup ring KQ. So to analyze monomial ideas in the KQ, then you need to then we can see ideas of the affine semigroups first. And indeed, as the slide header says, some algebraic properties of affine semigroups are determined by IQ, which is the polyhedral cone generated by non-negative real linear combinations of these generators. So to see such a relation, say let's spec Q be the set of all prime ideas of Q. We don't order by inclusion. So it is just set of all prime ideas in Q. So it corresponds to monomial prime ideas in the affine semigroup rings, but we can give some order by inclusion. And then you can see that each opposite poset is actually isomorphic to face lattice of the cone IQ as a poset. And this isomorphism is induced by sending a prime idea P to each complement and taking a span over the real numbers. So for example, in this picture actually describes the affine semigroups defined by 1, 0 and 0, 1. And it corresponds to a polynomial ring if by sending 1, 0 to x and 0, 1 to y. Well, if you're familiar with the graded algebra, then you can think of this 1, 0 and 0, 1 as a n2 grade of this polynomial ring kxy. Then if you think about the monomial prime ideal, for example, say monomial prime ideal generated by x, then you can see that all the standard monomial, so monomials outside of this ideal, are all in the y-axis, right? So by taking the span of these ideas, monomials outside of the monomial prime ideal, then you can get the face of the cone. So from this, we can actually define face of the affine semigroups by complement of its prime ideas, right? And also, this affine semigroups has some nice properties that if we think about the localization of Q, which is just the same localization of the ring, but now using the additive set. But if we think about localization of Q by an additive set, then it is always a localization by the minimal phase containing that set. So for example, if we localize our polynomial ring, or if we localize our affine semigroups by 1, 2, for example, then this 1, 2 gives us negative 1, negative 2, and negative 2, negative 4, and so on. But since we have generator 1, 0, and 0, 1, so we can just fill all other monomials outside of this first quadrant. So actually, this gives us the affine semigroups which is generated by 1, 0, minus 1, 0, and 0, 1, and minus 1, 0, which is just the localization of the polynomial ring by x and y, which is low-rank polynomial ring with 2 variables, right? So as you can see, so polynomial rings are one of the special cases of affine semigroup rings. And since affine semigroup ring has such a relation with the polyhedral cones, so it is actually an active topic for combinatorial commutative algebras, right? And I also want to introduce some non-trivial affine semigroup rings, which is not isomorphic to the polynomial rings. So here, in this case, it is generated by 2, 0, 3, 0, and 1, 1. So you can also rewrite it as a subring of the polynomial ring generated by x squared, x to the cube, and xy, right? And then we don't have x squared y or something like that in this row because we don't have 1, 0, right? So in this case, the lattice point of the cone is not equal to this affine semigroups. So from this, you can see that actually affine semigroup has much more richer structure than category of polyhedrons. And also, what I want to show in this talk is that given a quotient of this affine semigroup rings, Q by I, or given a quotient of this affine semigroup ring, Q over I, and I want to show which one is Cohen-Macaulay or which one is not Cohen-Macaulay using the standard pairs. Okay, so then now we know what the affine semigroups are, so we can see how quotient looks like. So when you see quotient looks like, then you can see that actually it is like onions. Definitely they don't stink or don't make you cry. However, they have layers like onions have. So for example, in the viewpoint of the y-axis, and you think then you can pick 2 layers from the faces of the cone to the ideas. And also in the viewpoint of x-axis, we have 2 layers from the faces of cone and to the ideas, right? So from this, you can actually decompose all the standard monomials in the layers using the translation of faces. So for example, in the case of R1, we can organize the faces of the y, the faces correspond to y-axis, and translation of this y-axis by x, and also we can organize by faces of x and its translations. So these decompositions are called standard pairs. And in case of R2, we can also do the same thing for this layer, the first layers. But for the second one, this is also outside of the idea. But if we use F1 to decompose this, then it meets the idea. Well, if we use F2 to decompose this, then it meets the ideal. So we cannot use F1 or F2 in this case. But in that case, we can still use the phase generated by F1 intersection F2, which is just vertex, to decompose this by one of the just independent singleton, right? So this set of those translations are called standard pairs. And one thing is good for us is that standard pairs are always finite. And from this, what we can see is that actually these standard pairs, so if we have the quotient of the affine semigroups, then we can always send it to a set of standard pairs, right? Then you can think of this standard pair as a contravariant functor, since, for example, in case of R1, we have 4 standard pairs, which is 2 is from red and 2 is from blue. But these blue ones came from the restriction of this blue one, which is just standard pair of R1 localized by X. So since it is localized by X, so we have -1, 0 in here. So all these standard monomials are added up. So in that case, our phase is just the x-axis itself. So, and then we have 2 standard pairs or 2 translation of the phases, which covers all the layers. Then actually these blue ones are restriction of these blue ones. And these red ones are also restriction of red ones, right? And likewise, or in case of R2, these red ones that came from the R2 standard pairs of the localization by R2 by F1, or this blue one is also came from the restriction of these standard pairs of R2 localized by F2. So yeah, I didn't expect that such a contravariant exists, but it definitely just came up. So from this, now you can see that actually the set of standard pairs always cover all the standard monomials in R1 or all the standard monomials in quotient of affine semigroups, right? So we can think it as kind of the Kloppen set. Then we can just group all the standard monomials or which appears in the localization and make a one space to analyze all the things at once. So that's the standard monomial space we can see in the picture. So in this example, those blue points are all the monomials which are standard in some localizations. So these all the blue points in the first quadrant came from R1, blue points in the second quadrant came from R1 localized by X, and these blue points in the first quadrant came from R1 localized by Y. Then you can think all the standard pairs came from those R1 or each localizations as a Kloppen set. Then you can generate its minimal open set, which partitions all those standard monomial in the space, right? And these are called grain. And also, since standard pairs are finite, so those grains are also finite. And chaff of the grain, which is surrounding this grain in the agricultural sense, is nothing but just set of localizations which contains these grains. So for example, given these green ones, its chaps are nothing but just R1 itself and R1 localized by X or R1 localized by Y because they are all alive in the localization. However, for example, in this violet one, when you localize it by F1, then it is actually deleted or it is absorbed in the ideas. Or if you localize by X, then it is also absorbed in the ideas. So in that case, its chap is only R2 itself. So, and you can denote such a chap using the phases because all the localization appearing in this context is just localization by a phase. Then from this, now you may ask, what all these kind of stuff are important about the Cohen-Macaulay needs? And let me explain this using the algebraic Cohen-Macaulay conditions. So indeed, algebraic Cohen-Macaulay conditions was known by Grossendig and Serre in 1967. So they actually found that a module M is Cohen-Macaulay if and only if a certain cohomology called local cohomology is 0 for all the indices except the crude dimension of the M. And in later years, in 1980s, Ishida actually suggested how to calculate this certain cohomology using the combinatorial information. So the Ishida complex is actually constructed by all the components are actually the direct sum of KQ affine semigroups localized by spaces, whose spaces actually has the dimension K. And the differentials are determined by just the direct sum of the canonical localization homomorphism with some sign changes, and this sign depends on the orientation of the polyhedral cone. So, and these differentials are all just denoted as just 1 and -1 matrices. Then Ishida actually shows that given a KQ module M, we can calculate this local cohomology by using M tensor with Ishida complex and taking the cohomology of that chain complexes. So if you're algebraicist, then you definitely think that, hey, we already have algebraic and macro criterion. Why do we matter about the combinatorial things? Then actually my answer is that actually indeed, even in our simplistic cases, it's two-dimensional ones, so it is very simple cases, but all the local cohomology usually comes up with infinitely generated modules. So yeah, it is annoying when you just find the infinitely generated module, especially when you use the computer. So that's why we are focusing on find the combinatorial criterion. And indeed, Hochster already has some solution about these cases. So he actually focused on the Hilbert series, and Hochster did on the special cases, the quotient of the polynomial rings. He can show that actually Hilbert series can be decomposed into finite sum of the rational functions. And what I do in this Cohen-Macaulay criterion for general quotient of affine semigroups is to find the decomposition of this Hilbert series with finite rational functions. And these grain and chop actually do such a jobs. For example, all these grains will appear in R1 localized by X, and R1 localized by Y. So it gives us the exact sequence 0, K squared 0 in its graded part. And all the monomials in blue ones actually came up in R1 and R1 localized by Y. So it gives us 0, K, 0. And since these all grains are finitely many, so we can just decompose our Hilbert series with finitely many components. And all these cohomologies are actually determined by the cohomology of the chop, by thinking chop as a polyhedral subcomplexes. So like Hochster did in the Stanley-Wilson ring, we've got the theorem that actually Hilbert series can be decomposed by the dimension of chop with the rational function over the grains. Therefore, our affine semigroup ring, quotient of affine semigroup ring by a monomial idea is Cohen-Macaulay if and only if the chop as a polyhedral complex has vanishing cohomology for all the dimensions I except the dimension of the KQ over I. This R is KQ over I. Sorry for the confusion. So in our example cases, grains with red and blue ones have exact, but this violet one has the non-zero cohomology at the zeroth point. Those cyan and orange and green ones had non-zero cohomology at the second component, first component and zero component in the violet one. So, and since dimension of R1 and R2 is +1, so, and for Hilbert series of the zeroth local cohomology of R2 is non-zero, but Hilbert series of the zeroth local cohomology of R1 is 0. So we can say that R1 is Cohen-Macaulay, but R2 is not. So the reason I want to have such a combinatorial criterion is to adopt this situation on the Sage math or some Macaulay tools, so that a lot of users actually can calculate the Cohen-Macaulay using that computational tools. So thank you for listening. And if you have any questions, please let me know.
Thank you, Byeongsu. Let us all give him a round of applause.